Okay, we're right back here. So what we've been talking about is, looking at what happens if I put some material inside a magnetic field. And so the very first experiments were done in the following fashion. So we've got a solenoid, and if I put a current through, you can see that there's a magnetic field that goes inside the solenoid. But what happens if I, instead of having air, or if this is a block of wood, I change this into something that is some magnetic material. So if instead of wood, I make this this material here magnetic, and I think I've lost it again. And this kind of a magnetic material. Okay. In that case, what happens? So what happens? Um, uh, magnetic material inside the solenoid. Okay. And this is something that you ought to have seen in 2041. But let me give you a minute or two to refresh this. So what happens if instead of some vacuum or some wood that I wound the solenoid in, place this in some magnetic material? What happens then to the field, magnetic field in this case, inside the material? I'll give you a minute or two. Actually, did people hear me at all? Or was I muted all this time? Okay. Okay, question is what happens in this solenoid if I put a magnetic material? Anyone know? You want to give it a shot? Okay. So okay, now I've got a few answers, and so Harry, Jeffrey, and Vinci, they're all saying stronger B field inside. So indeed, that is correct. Okay. So the thing is, in this case, we have, we put this magnetic material inside, and somehow we're getting a stronger field back. And one way to look at it, and that's something that you may have seen before, is then this notion that the B field caused by the blue solenoid inside this green material is causing some extra induced current over this material. Okay? So the B field then causes some induced current, which then enhances, because then it itself would be more or less become a solenoid, and then you're getting more field. So that was the original experiment, and in a way, you can think about this in in a very kind of atomic sense. So that's kind of the first picture that we can take a look at. So in a very early stages, this is even well beyond before they learned about um, the atoms and the electrons, is you can consider some material like this here. And indeed, if we can have all of these in a very similar sense as a dipole, induced dipole, let's suppose that all of these atoms do have some uh, magnetic moment. Okay, and so while generally they're kind of oriented in all different directions, as soon as I turn on a magnetic field, I can somehow get all of these currents to line up in such a way that there's some net magnetization. And so again, one way to see this is, for example, assuming that there are all these currents like these. Okay, and in this case, let's have them all move in this direction and have them all move in this direction as well. Okay. And again, in a very similar picture to the electric dipole, we have here, we've got canceling currents, right? This is just cancel, and these just cancel in such a way that the net contribution is that there's this surface current that is made out of the contributions only at the edges. So if I take all these small elements together, then anything inside the bulk is is something that wouldn't necessarily contribute. In this case, if I look at a very similar analogy, then same as how the charges at a conductor or even inside kind of a polarized material, is that then you expect the charges to be, or charge density to be, distributed among the surface. So here again we have a you know there's no net current, in the bulk, but there is some induced surface current. Okay, and so this will actually be something that we're going to take a look at. We're going to consider how this may work. Now, before I do so, I want to introduce the different kind of materials. The situation is slightly different from the dielectric case, and so one thing that you can do, you can actually study these materials, is that the magnetization is often, which I'll put in brackets, is often proportional to the field. Okay, let's call this B. And so what we have is that let's call this the magnetization is equals to some constant here we call permittivity, is proportional to some B. And in this case, what we have is we have several different types of materials. If this chi is bigger than 0, call these paramagnetic. If chi is smaller than 0, we call this diamagnetic. Okay, so these two general classes is whether, you know, the magnetization is in the direction of the field B, or whether it's in the opposite direction of B. So if you will, is it enhancing or is it you know, diminishing the field that goes inside? Now there's going to be a third. There's going to be a third class, actually called ferromagnetic. Ferromagnetic, and this is a special class of the paramagnetic ones that generally has slightly different properties. In particular, it has properties due to the memory effect. But you know, we're gonna discuss this a little bit later in a special context. So for now, let's just focus on paramagnetic and diamagnetic materials. So the first thing I want to do is give an example of you know of you know kind of like what kind of mechanism could produce the either diamagnetic or paramagnetic materials. So we're going to take a look at examples where, you know, to see, okay, how is it possible to, in the dipole case, how is it possible the stretching, okay, and the torquing that we saw for the dielectrics? Well, those two end up aligning the field. They align the field. But in this case, we actually have to take a look and see, okay, well, how can we get something that lines up with the field, okay, with paramagnetic, or something that actually, you know, opposes the field, which is the diamagnetic case. So let's take a look at some of these examples. Okay, so the first case that I want to discuss is is kind of a loop, a current loop that then, you know, there's a magnetic field that then pierces through it, but not exactly in a perpendicular or parallel way. So let's imagine the following. So if I look at the actual view of this one here, so this is a loop like this, and let's call this A, size B, and let's have a magnetic field that comes up. And it's going to look a little bit weird, but I'm going to draw a side view for you in a moment. Okay? And there's some angle in between here. So, you know, this is my best attempt at drawing something along the line of 3D. So there's a current going through, let's call this I. Okay. And so if I take a look at the side view, it's actually going to look like this. And so in this case, if the current goes, then the current goes in here, well, comes towards me, and the current goes away from me in this direction. Let's call this side A. Okay. And so we've got a setup here where now in this case, magnetic field points a particular angle, theta. Okay. So we have this situation now, and I'm gonna, you know, this would be a good moment to take a few minutes break. I'm gonna ask you during the break, I'm gonna ask you to analyze this situation and then tell me, okay, well, what's gonna happen in this case? How do we expect this setup to go? Okay, so let's come back in 5 minutes. So that would be 3:03 and 3:02, 3:03. That's fine. And then we're going to take a closer look at this situation. So what happens in this situation, and if you will, if you want to take it one step further, is this paramagnetic or diamagnetic? Okay. See everyone in a few minutes. Okay, welcome back. So I do hope you've taken this 5 minutes to actually take a look at the situation and at least think alongside of what do I expect to happen. So let's take a look. Okay, we have a particular current going through, and so the first thing that we can ask is, okay, I've got a current, I've got a magnetic field. So what happens? There ought to be some forces, right? In this case, you know, on the sides A, right? Sides marked A. Where are where the forces pointing towards? Can anyone tell me? Left. Okay. So the side, this one, you mean, Jason? This one marked with the yes. Okay. What about this one then? Okay, that one points to the right. Very good. Okay, so we've got one pointing to the left, one pointing to the right. Okay, got this one, some F here, some F here. Okay, what about the top and the bottom? So there's one marked with a B, and then the opposite side. Okay, either Jason or anyone else? What about the force on this one and this one here? Anybody? So Alex says up for the upper wire, while down. Okay, it's a little bit hard to think about it in 3D. Let's think about. Let's look at this figure then, Alex. Okay, so we've just covered this side A, and then we can ask, okay, well, what about um, what about the force on these two wires here? Out left upper wire, good. Same as Harry. Left for the current coming out, upper wire. So in this direction, there's an F. And what about this one? Right, very good. Excellent. Okay, so we've drawn in some of the forces, and you can hopefully more or less guess where I want to go towards. But in this case, what do we have? Well, we have a torque. Right? So we have one going to the left, one going to the right, and then we have a net. We have some net torque. So in this case, what is uh, well, you look at the main direction of the torque. So this is N. Okay? So that would be something along the lines of A. Right? So it's half a for each, but then you've got two of them. So it's A, and then the force, and then some sine theta. And if you will, we can give it, we can give it some directionality. Let's call this X. And then the question is, okay, well, what about the force itself? Well, that's just the current times the length, oops, direction, and then the field itself, B. So all with all, we've got that the N is just I AB sine theta in the x-ray. Cosine? Okay, fine. Changes. Theta. Okay, you're right. I'm sure you guys are probably much faster with these sites and things, cosines. Well, actually, no. Sorry, that's not the right angle either. Yeah, angle between the normal. Yes, that's right. I was gonna just that one because the normal. I've lost touch again. Excellent. Okay, I'm very, very happy that people are actually thinking along with me. So this one, the normal. I'm actually going to need this in a moment. That should be theta, because if I look at this picture over here, then this is the direction where M is. This is the direction of the magnetic moment if I take this current loop. Very good. Thank you very much, Alex. And so if I take a look at this, N equals, well, actually, I don't need the magnitude for this one. Here and here, this, as I put a direction in here. And so indeed here we can end up with you know, just saying that this is M is M, okay, because that's IAB. So that's I times the area in this case. So that's M. That's the magnetic dipole moment that we've seen before a couple of lectures ago. B sine theta in the x direction. And so just by analyzing this situation, what are we dealing with? You know, how does the magnetization, how is that going to align with the B? So just going back to last slide. So the question is, are we talking about a paramagnetic, I wouldn't say force, but paramagnetic mechanism, or are we talking about the diamagnetic? So Alex indeed saying that it's paramagnetic because the B field aligns with M in the direction to B. That's right, right? So in this case, this tilt, this torque is causing B to line up, sorry, causing M to line up with B. In this case, this would be paramagnetic. Very good. So you know, we've more or less, and you know, we've more or less looked at the mechanism through which, you know, if there is some existing current loop, some dipole, some magnetic dipole moment, then you know the torque will cause the moment to line up with B. So the magnetization is in the same direction as B, and so in this case, if I consider this to be proportional, then this chi should be a positive constant. Good. Now, before I move on, I just want to iterate something. I just want to make people understand. So some of the examples that I'm giving here are highly classical. Okay? And so we assume indeed some current loop and some B field and so on. But of course, we have to realize that when we talk about atoms, molecules, particular kind of, you know, the current loops, they are fundamentally quantum mechanical. And they, when we talk about electrons inside atoms and inside molecules, they behave quantum mechanically. And so, what I'm presenting here and what I'll do in a moment is more or less just to give you a sense that you have a feeling, physical picture where these effects come from. A proper treatment instead should come from quantum mechanics, and that's something that I believe, I recall properly, you should be learning also in your quantum mechanics course. I forgot the exact code for that course, but and that's something that you'll learn. If not now, then next year. But within the scope of this lecture series, of course, I can't go into too much of the quantum mechanics, even though when we discuss ferromagnetism, you know, we will discuss that a little bit. Okay, so take this as a classical analogy, or more or less kind of a classical intuition for which you can understand, appreciate where things like paramagnetism and diamagnetism come from. Okay, so let's move on. Let's take a look at another mechanism. So in this case, what I'm going to assume is, again, it's a very classical picture. I've got a circle like this, and this is my strawman picture of an atom where I've got some nucleus, some proton, and this is some electron whizzing around it in an orbit. Okay, and then the question again is, well, what if I have a field here, through it? In this case, what's going to happen? And so for this one, the first thing that we want to look up is the current, of course. Well, if in this very simplistic picture, the current can of course be considered as just the amount of charge, in this case minus E, okay, because the electron is negative, divided by the period of of it going around this orbit. In this case, this is just negative v is the speed at which it goes, and then you got 2 pi big R here. That's the amount of time it takes to go around one loop, and so the current is more or less given by the period which this electron goes around. Okay. Now, so the moment itself, m, is just given by I times the area of this. That's m r squared, sorry, pi r squared. Now, I have an expression for I now in this case. And so in this case, what is it? I get that it is minus e r over 2. And if you will, I can give this some directionality by putting everything in the z direction. Okay, so in this case, I've got some current, I've got some current going around, and then the question is, what happens in this case if I now add a field, magnetic field? Okay, so imagine the field going. Imagine the field going up. So now let's make this green. I've got a field going, up. Okay, and B field going up. So again, why don't I give you 5 minutes to look at this question, consider this scenario, and then try to see what's going to happen now to this orbit, or what's going to happen to this. Okay, so we'll come back in a quick second, 5 minutes. We will consider this scenario. So let's come back at 3:30. It's 3:20. Okay, see you guys in a bit. Okay, welcome back. So again, I hope you've taken these few minutes to analyze this situation and at least give you some sense yourself, some sense of what's gonna happen. And so the first thing that we can take a look at is, of course, the centripetal force in this case, right? So we can take a look at how is this how is this electron going to be uh, how is this going to be affected uh, by, by this motion indeed. Okay, so let's take a look. Okay, let's take a look at the this. And so in this case, let me ask you, okay, what's the centripetal force here? Can anyone tell me if I were to balance the centripetal forces, then what would I get? So the first thing that we should look at here is the is the inward forces. So if there was no magnetic field, no magnetic field, in this case there are two balancing forces. Okay, so we've got the electron and the positive nucleus, and so the two balancing forces are the electric force, and then that should equal to the centripetal force. In this case, what do I have? Space for myself. Okay. So here I've got Ke squared over R squared. That equals to the mass of the electron squared over R. Okay, so that's something I hope you the origin of, right? So if there's no magnetic field, then the centripetal force is only sustained by the electric force, which is then balanced by of course the centrifugal force itself. Okay? And so we can now analyze this one more. So if there is a magnetic field, so if there's a magnetic field, what happens then? What is the additional contribution if I suddenly add a magnetic field here? Start with right. Original electrostatic force. Anyone? What is the additional force here? EVB. Okay, good. In which direction? Plus, minus. Right. Let's see. In this case, the current. Okay, yeah. Here we need to be a little bit careful with our thinking, but that is well, okay. That is in principle fine. Let me just start with EV, and I'll make sure to get the signs correctly. So anyway, don't worry too much about the signs for the time being. I'll I'll get that checked out, because we have to make sure that that's a negative charge. And so let's see. Okay, so let's leave it like this for the time being. But the thing to note indeed is that there is now an extra contribution EVB. Okay? And so something is going to happen to this orbit, where originally it is only sustained by the electric, electrostatic force. We now have an additional contribution to the to the force, right? So in this case, if this is, then that is the current. It goes this way, and yes, it should be a -1. Yeah, right. Okay. Change this, because the example that I prepared is actually the other way around, so I don't constantly get confused with. Make it this way. In which case, I is going in this direction. No, wait. No, that should be right. Yes. If I get this correctly, if I put my hand here, this is the current goes in this direction. It goes inside. Oh, wait, no, I have to use my other hand. It's the right hand rule. Okay. You are completely right. Let's do it this way. Let's do it this way. Is it better to indicate the current direction? Yeah, oh, no, you're absolutely right. Okay, let's make the current go around this way. Current going in this direction. Sorry, this is the electron direction. So the current goes in the other side, other direction. And then the field is going out. So I have to do this with my right hand. Okay. And so in this case, the force is in the same direction as the electrostatic one. Okay. Everyone follows this still? Okay. Anyway, minus signs, just that's also not my forte, but this scenario should be okay. Anyway, it doesn't matter, right? Even if I do it flip the other way around, I just have to make sure I keep track of the minus signs. So in this case, let's take a look at what we're supposed to get. Okay, so we've got with magnetic field and without magnetic field, and so now my V will have changed. Right. So suppose I can only keep it in a fixed orbit with R, which given the the fixed orbits that I'm allowed to have, then the only thing that you can do is change the velocity of this system. And so we can calculate, well, okay, how much does the velocity change? And so if I take the top and the bottom equation and I end up subtracting them one from the other, I get that. Yeah. I get that. EV equals to ME divided by R V dash, V dash V. Okay, so V hat minus V squared. So this is what's going to happen with V, And so if I write this now as ME over R plus V, and so in this case, I've just rewritten this one as the expanded the product. Okay, so now we're going to make the assumption V is approximately V, okay, close to, but not identical. In which case, what do I get? I get that this becomes 2V, this becomes delta V, and this becomes V. So I got EV minus this one ME over R. So this is 2V and delta V. So then indeed, I can calculate what the change in V is. It's just ERB, correctly, ERB, yes, and then over 2ME. Okay. And so now the rate of change of M, so we find out what is the change in M given a change in V. Well, that is just given by minus a half E. This is delta V RZ here. And this comes from this expression that we've gotten here. So in this case, again, right, when we look at this situation, what we're seeing is that given a particular delta V, my delta M is actually changing in the opposite direction. So the change in M is going down, right? Because we can now rewrite this delta V here as E squared R squared 4ME. So depending on the direction of B, right? And in this case, we're getting a negative sign. We must have it in such a way that the must have it in such a way that change in M is in the opposite sign of B. And so in a structure like this, in this mechanism here, where we have a field piercing through the orbit, then the influence of having a B field on the orbit is to slow it down. And if I slow it down, I get that the current goes down, okay, in such a way that when the current goes down, my magnetic moment goes down. And so I'm weakening, existing magnetic dipole moment. By adding a B, I'm actually weakening magnetization in that direction. So I just want to give you again, right? This is not fully in a quantum mechanical sense of what is happening. And in order to fully understand what is happening, we will have to go to the quantum mechanical picture, which is beyond the scope of this lecture course. But you know, there are multiple ways in which a B field will affect the both the alignment of an existing kind of magnetic, you know, magnetic dipole, as well as the actual magnitude of this dipole moment. And these two contravening mechanisms. So one is paramagnetic in this case. Here we've got some that is diamagnetic. The extent to which you can do this, okay, the extent to which you can, the paramagnetic contributions and the diamagnetic contributions will then set out to be the total property of this material. And then, we have to look at a lot of different factors that then factor in. And so the situation is fairly complex, right? For a single material, it's you will have to measure, and then through different arguments regarding the maybe the lattice of my of my my material, but also on the electron spin, how many spin vacancies are there so that you get the spin of the electron, and how many free of them are there, how many are actually being paired up in a quantum mechanical sense. That's all these factors are going to lay out and going to influence the total property of this material. Okay? So again, I can't stress this enough. This is merely just a just giving you two examples through which you can influence in a classical sense. That the real scenario or the real situation is actually quantum mechanical, and um, and in that case, it really depends on quantum mechanical properties, like where the spin aligned, how many free spin spaces do you have, what is the spin interaction. Okay, so when we discuss ferromagnetism, we'll see that this critically depends on exchange. I wouldn't call it force, but the exchange Hamiltonian, right, between two spin sites, and then it depends on how much overlap is there between electron wave function. So in such a way that we know we can calculate how much spin, how much a spin interaction contributes. Okay, let's take another kind of take another 5-minute break here, and then when we come back, we'll kind of close it out by looking in a very similar way to what we've seen in the scalar potential case, is how do we rewrite the vector potential now in light of a magnetization. So okay, so are we inducing, in this case, more or less of a magnetic dipole moment inside the material? And then we'll close off the lecture with a full description of the Maxwell's equations, in this case, in matter. Okay, so let's take a 5-minute break. So let's reconvene at 3:47. Everyone in a moment. Okay, let's get back to it. Let's see. Alex is asking, what if we change the direction of the electron current so that the magnetic moment is aligned with the B field? Okay, so maybe I didn't you know, explain this very well, but basically, depending on the magnetic moment, so either whether the field is if the field is aligned, just draw it up. Okay, if the field is aligned with the magnetic moment, this. So nice full circle. Okay, so let's see. This is R, and we have an electron whizzing around. The thing is, you gotta make sure here that you don't fall into the two negatives. So if this is the electron here, and um, this is R, so in this case the current goes in the other direction. This is the current I, and if I take, let's see, I have to do this properly as well. So the M, let's have M in. I have to make sure that surface is defined in a. I define the surface in a right-hand fashion. The current goes this way, then the magnetic moment goes down. Magnetic moment is in the downwards direction. And so if the B field is, right, I hope that is clear. So in the direction of the current, then the right-hand side, and this is what the magnetic moment is in that direction. Because I think what you're trying to say is, oh, what if I now change the direction of the current, right? But if I keep M to be in the opposite direction, then I have to make it consistent. One way to do it is to say, okay, I only use my right hand, and so my right hand, if this is the current, then this downwards is the magnetic moment. And so if the magnetic field is in the opposite direction, then okay, so if this is the M, so now if I turn around and say B comes up, so it's the opposite direction. This is the current, my field comes in, so then the force is going this way. If the field is in the same direction, then we are doing this one, and the force is going that way. Got this right. Yeah. And then in one case, so if it's going upwards, then I am decreasing my force, my balancing force, in which case my velocity should go down. And if the velocity goes down, then the current goes down. And if the current goes down, then M goes down. That's right. If it is in the Yeah. So in this case, there's a double negative. I just need to make sure I explain this properly. So if it's in the B field, if it's now in the if the B field is aligned with it, then I have a stronger um, then I have a stronger if the field is now in the same direction. So this is Z. The B field is in a negative Z direction. Then I flip the sign. But then the velocity goes in the opposite sign as well. Right? The velocity goes. I've got my delta V here. So I've got two things flipping, right? I've got my speed going, up or down, and then the B field being in the same direction or in the opposite direction. And those are then the two negatives or the two positives that then get flipped that way. And so if you do this properly, and that's something that I do encourage you to do it at home, then it doesn't matter which way the field is. You will end up, as long as there's something there, you will end up slowing this whole thing down. Okay, it's a little bit a long and contrived explanation, but I hope that is reasonably clear. Okay, let's move on. We have a little bit of time left today. So the point where we were is here. So last time we also showed that when we considered the following, so we've considered some matter distribution, and we have three different length scales. Okay, so or three different scales in vector space. So let's say here, here, and then somewhere here. So this is my site. Okay, so this is the entire distribution of matter that I want. And then I can label all of these three with R, color. Okay, that's R. And then this is going to be R prime. And then we have a third scale, which is just integrating over a site of some magnetized material. And so we've got these three scales that we consider again. And so what we have now is that the vector potential here, A, is just mu naught 4 pi and just the integral of J. There's double prime R double prime E double prime divided by R minus R prime minus R double prime. Okay? And so we can do the exact same expansion that we did before. So again, recall that the expansion that I did was R minus R prime minus R double prime. I'll label these with J because this is the J site. Here I can do the following expansion. I can write that this is 1 over 1 over R minus R prime J. Okay, and then we get along the lines of 1 plus, and then we have other things. No, sorry. Extension. Okay, and then R minus R J prime times R double prime J divided by R minus R J prime over 3. right? And so on and so on. And so in this case, again, we're doing exactly the same as we did last time around. And so we can write the vector potential now of the following form. So I got mu naught over 4 pi, and then the sum of all the sites that I want to visit in my magnetized material. I've got r minus r prime, j, and then the integral of j r double prime dv double prime. So that's the first term. And then we have the second term. Again, let me just write mu 4 pi and the sum of all the sides. And I've got r minus rj divided by r minus rj cubed. Integral, again, over all of the material. And I've got r double prime j r double prime double prime. Okay. So again, this is what we did last time with the scalar potential, and we can do the same thing now with the vector potential. And of course, there are other terms here that we won't consider. Okay, so the first term here, this one, we can set this to be 0 if I have conservation of charge. Right? So we're talking about static situations. So again, in general, there's no net, accumulation of charges inside this. So this is just conservation of charge. Now this part over here, this part over here, together with this part over here, I can actually end up rewriting this, and this is actually important. I can end up rewriting this part. And again, I don't think I have time today to fully get into this, but I can write, well, firstly say that j, the integral of j double prime j 0, okay, and this is the conservation of charge. And then the other term that I can rewrite is this term here, r minus r j over r minus r j cubed, and then the integral of r double prime j d. This, I can rewrite this as m. This is actually very similar to the way we derived this m very early on in our multipole expansion. Derive this, and this is cross r minus r prime j divided by r minus rj cubed. Okay, this is just some vector algebra. The details are not terribly important, but I can rewrite the second term to just be the magnetic dipole moment cross this factor here in this expansion. Okay. And so ultimately I end up with the first term here being 0, and then the second term being the cross product here. And so A is just mu naught over 4 pi sum of all the j's of m j. Okay, so that's the magnetic moment of the jth side. R minus rj prime divided by r minus r prime j cubed. So again, what we've done literally here is just integrating over the double prime coordinates so that I now have the average contribution over a single site, which is j. Again, I can write mj Okay, just going towards some m, some density times times some volume j, in such a way that I let everything go to I let Vj goes to 0 and a going to infinity. And so basically this here just turns into an integral. So I can end up writing this a as just mu naught 4 pi integral m here cross, again, this term now here, but this term last time around, we saw that we can write this as the gradient of this r minus r prime. More here, right? Okay. And so we end up in the same situation where we have we are now, instead of having a dot product here, we have a cross product here. Again, we can do some algebra, do some vector algebra. So for example, I could use that the curl of some m r minus, actually, let me do it on the next page. I can rewrite this further. So I can consider that the curl of m r minus r prime like this here is just 1 over r minus r prime curl of m plus gradient of 1 over r minus r prime times the curl. Okay. And so in this case, I can use a relationship like this, but also the other thing that I need is this one over here. So I have that integral some m over r minus r prime equals minus integral of let's see, 1 over r minus r prime m cross ds. So using this one, these two here, and I insert it into this expression over here, I can do some algebra and I end up with the following expression. A equals mu naught 4 pi here, and this is just this term that I had here, r minus r 1 over r minus r prime m cross ds plus mu naught 4 pi integral 1 over r minus r prime. Now I've got curl of m. Right. Okay, so we end up with almost the identical situation, as long as I recognize that I've got something here that looks like a surface current, right? It's the current, so it's 1 over r contribution to what a. So here we expect some some surface current, right? Because we only have to integrate over the surface. And the same, we have here something that then looks like a volume current, density, both of them, because this is integrated over the volume. And again, I can identify some surface current density, which is just m cross n hat, okay, because this s here is just ds n hat. and some here, which is just the curl of it. So I basically have two, again, I have two contributions. I have a particular surface, current that I induced. And remember the picture that I drew early on here. So indeed, when I magnetize this, when I have all the loops going around in the same direction, then typically what I have is both a surface current that just goes along the surface, and apparently, if there is a curl of this magnetization, then there's also some volume surface current. And so we end up with, the final realization. It's more or less a recap then. So if I have a polarization, well, then I get both a surface charge density, which is P dotted with n hat, and some charge density in the bulk. And if I talk about magnetization, then I end up with the following. K is K M equals M cross N, and J equals the curl of M. Okay. So in both cases, so either I have polarization of a dielectric material, or I have magnetization of a magnetic material, I end up with, globally, two different types of contributions. One is on the surface. In the polarization case, it's just the charge density. And then in the magnetization case, it's a current density, either surface or volume density. And so these two cases are completely analogous to each other. And of course, the details will depend on what extent we have this magnetization field, what is polarization field, P or M. Now, finally, we can also take all of this and now consider the total charge. Okay. So here, now, the total charge would be the free charges minus the, or plus, but this expression is minus the bound charges. Write this a little bit clearer. This is plus rho p, which is just rho, the free charges minus use, volume charge, and similarly total current, just the free current plus magnetized current, or the bound current, equals to A free plus the cross of the magnetization. And all of this then allows us to rewrite Maxwell's equations in a particular way. So in this case, I know that in this case, I have that for Maxwell's equations, I've got that the divergence of E equals rho over epsilon naught. In this case, it's 1 over epsilon naught rho free minus the divergence of P. Now I can rearrange the divergence of P to be to the other side. So I've got rho free equals to the divergence of epsilon naught I put here minus P. And this I can now call divergence of D. Okay, and you should have seen this in 214, where in this case D is just defined to be epsilon naught plus P. Okay. Similarly, I can write curl of B is just mu naught J free current plus the curl of M, or I can now rewrite the curl of M on the other side, and so I get that mu J free equals to the curl of B. Okay, actually, no. On the other side, not here, and then minus M. And this here I can call curl of H in such a way that H is just 1 over mu naught minus M. And so all with all together, I can now write Maxwell's equations. Maxwell's equations in matter are basically the divergence of D is rho free. I can write that the curl of E is 0. Divergence of B remains 0, and that the curl of H equals J free. Okay, so these are Maxwell's equations in matter, and if you will, you're perfectly able to write these in the integral form, just using Gauss's theorem and Stokes' theorem. Okay, so this is basically the framework that we're going to be working with when we consider materials. So this is both a polarization and a magnetization. And they end up changing the Maxwell's equations in terms of the thinking in free charge and free current. And so next week, what we're going to do is we're going to actually take a look at some examples of, how do we now solve Maxwell's equations or the Poisson and Laplace equations in these cases, where we have, for example, different materials possibly stacked upon each other, and so that the field pierces through, And so in order to do that, in order to do the solution, again, remember that we must know the boundary conditions. So we're first going to take a look at the boundary conditions for these dielectric materials and magnetic materials. And then we're going to expand upon what we've learned earlier in the solutions, right? And how to solve Poisson and Laplace equations. And we're going to take a look at how to do it under the boundary conditions that are imposed by different materials or interface between different materials. Okay, so that ends it for today. My apologies, it's a little bit possibly confusing. Quite a lot of this is inspired by some of the examples from Griffith. So if it wasn't fully clear today, take a look at the discussion in Griffiths. But on the other hand, the derivation of the free charge and the free current, that's the basis on which we're going to continue on. The examples that I gave last week and this week is really more to give you a sense of a physical intuition of how to either get paramagnetism or diamagnetism in materials, but the actual material, the actual kind of bulk of being able to do the calculations are summarized here in Maxwell's equations. Okay, so let me close it out here and see if there are any questions. So Alex is talking about the signs. Yeah, you need to. It's a little bit.
No. Sorry, I'm not talking about the diamagnetism. What I mean is that for the electric displacement and also the auxiliary field, you because we just combine. Let me see. May you go back to, I think, page 12 or page 13? 12.
Okay, 1 second. I need to count. Fear says, Dean 12. There's this one.
Yes. I'm thinking about because for the bounded charge, the nabla is actually in the primed coordinates, but you have just take out the prime for the coordinates, and although it seems to be correct for the sign, but I'm not sure about why we can just take away the prime coordinate, because if we treat the prime nabla as nabla, we have to multiply a negative sign, right?
Right. Yeah. So if I do this properly, no, that is confusing. And to answer Jeffrey and Lee Shunji, I will, for this stuff, I will also provide typed up lecture notes. So don't worry about it too much. On the other hand, please also take a look at, all of the textbooks have the same things. So you can find the answer there as well. The problem, well, not the problem. The thing here is that this one here is a prime nabla. Okay. And so did I miss any? Did I miss any of these? Prime nabla or unprime nabla?
Yes, and in this page, all the nabla are not primed, so I'm quite confused, I think.
Yeah. No, you're right. Okay, I need to do this properly. So this one is a prime nabla, but just bear in mind that whenever I'm operating on r minus r prime, I can always flip the nabla and do the signs properly. But you're right. This is something that is important. You need to make sure that these signs are done properly. So this is not a prime nabla. Then this is still correct. But this one, I should be able to flip to an unprimed, a prime nabla. This. I hope I can do this on the spot quickly enough. Okay. And so if I want to do this one here, so this would be a minus. So then this here would end up being a, let's see, this one here, yeah. So I should be able to flip it like this, okay? And so I can now get an expression of this one, which is a primed nabla, in terms of unprimed nabla and unprimed nabla.
Oh, okay. Perhaps I work it out at home by myself again.
Yeah, just if you're confused, just put it on the discussion board. I can I can check the maths exactly, but it would take a little bit of time for me to here in front of you work it out exactly with all the different minus signs and not minus signs. But just for your information, like this would be the way in which you can turn if you start with an unprimed nabla to then when it only operates on 1 over r minus r prime, you can flip the nablas. Sorry, yeah, you can flip the nabla to prime to unprime, but with a minus sign. Okay. Yeah, apologize for the for some of the confusion. It is something that you need to be very careful which primed and unprimed you're taking. I'll try to make sure when I type it up that I keep track of the primed and unprimed. But these, the end result, those should be the ones that are unambiguous, right? So you've got the JM, which is the current in the bulk due to a magnetization, is just the curl of this M itself. And the same thing goes here with polarization. Those are those I think the signs for those should be correct. But yeah, how do we get there and exactly how to do all the vector algebra? That's something that when I type it out, I'll make sure it's correct. Okay. Any more questions? No, Alex. I mean, if it isn't clear, then it is important that this is clear. So you're absolutely right to ask about it. So in the second, Harry's asking on the second last slide, is there a bracket missing on the right-hand side of the L cross B? Bracket missing. Uh, yes. Correct. Um, yes. Should be this. And then I can now do this. This B. You're right. Very good. Okay. Going once. Going twice. No more hands up. Sure. Go first. Slide 6. This one. Okay. Ask away, Harry. Okay. Yeah, you may be right. Um, I always get confused as well. I should have used the left hand instead of the right hand. Let's see. This F is V cross B. So V is in that direction. V cross B way, it should be V cross B. Yeah, you're right. Okay, yeah, I think I made the the directions are reversed. You're right. Sometimes I even forget which hand to use. It's the left hand rule if I want to use this being the current, my palm being the field, and my thumb being the force. Or it's V cross B, but using the right hand. So it's V is in that direction. B is in this direction. B is into the paper, so it's V cross B is up. Yeah, you're right. Okay. Me. This is why I sometimes get confused. Let me change it here, like this, for the time being. That is easier. Now again, good question, right? If it isn't clear, even if I say something wrong, right? Ask. Yeah, what I can encourage you is just go through it and do it again for yourself. I may have flipped the signs here and there. Again, like I said, sometimes I get confused which hand. But you should be able to, if you do it consistently, you should be able to get this right. And again, when I type up the notes for these, I'll make sure to double check the hands. But this specific example comes from Griffiths, so take a look at Griffiths and you can see the. Anything else? Okay. Not, let me stop the recording.